we have that we should calculate the value of electropotential for tin and beryllium. So we have been given that E cathode is minus 1.99, E anode is minus 0.14. So the question is, which of them is E cathode and which is E anode? That is the question. Looking at what we have there, we can see that tin is being oxidized while beryllium is being reduced. So if tin is oxidized and beryllium is reduced, which of them will have that value? So it tells us that as tin is oxidized, beryllium is reduced, minus 0.14 is closer to being a positive value compared to minus 1.99. And when you are closer to being a positive value, it means you are the reduction. So it means you are the reduction potential. So minus 0.14 is closer to the positive value. It means it's going to be the reduction potential, while minus 1.99 is the oxidation potential. So looking at that, from our value given to us, first, from the equation, we are told that tin has been oxidized from 0 to plus 2. Beryllium has been reduced from plus 2 to 0. That is the equation. So we need to go by the equation. And we are told that E cathode is negative 1.99. E cathode is negative 1.99. E anode is negative 1.4. And that is what we have. Negative 0.14, I beg your pardon. (0.14), and that is what we have there. So having seen tin being oxidized from the equation, beryllium being reduced, so it simply tells us that the value that will be assigned to each of them will be that for cathode and anode. So tin has been oxidized. Which of this is the value for tin, since tin has been oxidized? Oxidation takes place at the anode. Oxidation takes place at the anode, while reduction takes place at the cathode. So from what we have there, it tells us that beryllium has been reduced. So since beryllium has been reduced, reduction takes place at the cathode and oxidation takes place at the anode. So what we simply have to do is, tin is being oxidized. As tin is being oxidized, oxidation takes place at the anode. So E naught is going to be E reduction minus E oxidation. So E is going to give us, E reduction is for cathode, the cathode, which is minus 1.99. That is for the cathode. And then minus E oxidation. Oxidation takes place at the anode. This will be minus 0.14. So this is E naught equals to minus 1.99 plus 0.14. So E naught is going to give us minus 1.99 plus 0.14. Or we can say 0.14 minus 1.99. So it's still the same. So this is giving us 0.14 minus 1.99. That gives us minus 1.85. So we have minus 1.85. So this is what it is. So we can see that since our E naught is negative, it tells us that that cell also isn't going to be feasible. That is to say, it's not going to be spontaneous. The reaction isn't going to be feasible, or the cell is not going to be a spontaneous cell. The reaction won't be spontaneous, because for E to be spontaneous, then these values have to be positive. So that is how to calculate our values for E. That is our electromotive force, or our electropotential. That's our electropotential value. So we are done with that. Now, away from that, we can now see what do we mean by the spontaneity of a reaction. How can we determine if a reaction or a cell will be spontaneous? That is what we are going to look at next. So to determine the spontaneity of a reaction, from our knowledge in rate of reaction, we know that if the electropotential is negative, then reaction is not going to be spontaneous, just as we just calculated in the last example. If the electropotential E naught is negative, the reaction isn't going to be spontaneous. But if it is positive, then the reaction will be spontaneous. The question now is, why? Why would the reaction be spontaneous if E is positive? It's going to be spontaneous if E is positive because we can recall that E being positive is that it is greater than 0. And from our rate of reaction knowledge, we have been told that delta G is equal to minus NF E naught. So our delta G is equal to, if our delta G is going to be spontaneous, it must be this. So if we have delta G equals minus, in this case here, let's say we have 2 moles of electron times Faraday. Faraday is 96,500. Then times, in the case of this value we have here, minus 1.85. Minus 1.85. Now let's see what our delta G value will be. This is going to be minus 1.85. As we can see, minus 1.85 times 96,200, 96,500 rather. Okay, let's do that again. 96,500 times, we have our next minus 1.85, minus 1.85, okay, negative 1.85, and then times 2. We can say that gives us this. Then times 1. When we say times negative 1, times negative 1 will give us negative of that answer. So we're going to definitely have minus 35705. So it tells us that at the end of all this, we are going to have a positive answer, which is 35705. So our delta G is positive. So if our delta G is positive, it tells us that the reaction is not spontaneous. For reaction to be spontaneous, delta G must be a negative value. So if delta G must be negative, then it means our E must be positive. If delta G must be negative. But if our E is negative, then it's going to multiply with the other negative, and then it makes our delta G to be positive, which means the reaction isn't going to be a spontaneous reaction. So this is actually how we know the spontaneity of a given reaction. So if a reaction is going to be spontaneous, then our E, the electropotential, must be positive. But if it's negative, it will not be spontaneous. So that is how to determine the spontaneity of a given reaction. With that, we shall just take few examples, just as we've seen before. So look at between zinc and copper. If our E is positive, then it means that the spontaneity of the reaction is sure. And if, on the other hand, the electrodes are to be changed, that is to say, zinc will be at the right instead of left, and copper at the left instead of right, then it means our E value is going to be minus 1.10, and it therefore implies that delta G will be positive. And if delta G is positive, it means the reaction isn't going to be spontaneous. So that is that. Now we look at example 2. Let's look at example 2. Says a voltaic cell that uses silver and tin. A voltaic cell that uses silver and tin is being constructed, and we are told to identify the anode and cathode. We are told to also calculate the standard cell potential, write the balance equation for the overall cell reaction, and we are told to state the spontaneity status. So we are going to state the spontaneity status. So what is the spontaneity status for this? That is what we are told to do. Okay, so let's proceed to looking at how to do that. First, we need to identify the anode and the cathode. So which of silver and tin is going to be the anode and cathode? First, we need to write out their electrode potential values. From the previous calculations, we know that silver is 0.8 volts, or you may say 0.80 volt. That's for silver. And tin, silver is positive. Tin, we just saw in the last calculation that tin is minus 1.37 or 1.4. So it's usually 1.37 or 1.4. That is tin. So having seen that, it is good. We know that this is for tin. So we can see that for tin. So it is clear. So tin is minus 1.37 volts, while silver is plus 0.80. So this is for tin and silver. So with that now, what do? We need to go ahead in solving that. So tin is minus 0.13. Minus 0.13. Not just minus that, minus 0.13. Sorry about that. So that is for tin. So minus 0.13 or minus 0.14. Sometimes it is written as minus 0.14. So, but we have it as minus 0.137. So with this now, how do we go about that? The first thing is to identify the anode and cathode. So which of silver and tin is going to be the anode and which is going to be the cathode? So we can see silver is positive. Since silver is positive, automatically that makes silver the reduction potential. So silver, since it is plus 0.8, this is reduction, because the more you are positive, then the more likely you are reduction potential. So silver is 0.8 and that makes it reduction, and tin is minus 0.137 volts, that makes it oxidation. since it is oxidation, what takes place at the which of these processes takes place at the cathode and which takes place at the anode? Oxidation is loss of electron, and loss of electron takes place at the anode. Reduction is gain of electron, and gain of electron takes place at the cathode. So that is actually what we've talked about. Reduction is gain of electron. So, and it takes place at the cathode. While oxidation is loss of electron. Loss of electron takes place at the anode. So this is actually between tin and silver. So we have talked about the first one. We've identified anode and cathode. The next question says calculate the standard cell potential. So the standard cell potential for silver and cathode is going to be E0 is equal to E reduction minus E oxidation. So this is going to be E0 equals to, the reduction is silver, that is 0.8, minus oxidation is tin, that is minus 0.137. So this is going to be 0.80 plus 0.137. So we have it as, so let's go to our calculator. We have it as 0.8 plus 0.137. So that gives us 0.937. 0.937. So approximately 0.94 volts. So our electropotential is 0.94 volt. So we have seen that. It's as simple as that. And then next we have write the balanced equation for the overall cell reaction that occurs. The balanced equation. So we need to go ahead to write the balanced equation now. How do we do that? This is how we go about that. Between silver and tin, since silver is reduction and tin is oxidation, so reduction has to be written at the right hand side and oxidation will be written at the left hand side. Since tin is oxidation, we have to write tin this way. So we'll go that way. Tin is oxidation, so it goes from 0 to SN2 plus, the salt bridge, and then silver will be Ag plus, and this. But it is worthy to note here, this is just the cell representation. But if we are to write the full equation, this is now going to be Sn plus Ag plus, that gives us Sn2 plus and Ag. So we can see that. So this tells us simply that though tin actually lost 2 electrons and silver will gain those 2 electrons. That is what it tells us. So we have to put 2 here. Tin lost 2 electrons and silver will gain those 2 electrons. That is actually what it tells us here. So this is the full equation for that reaction. It's as simple as that. So we have 2 here too. So that is how it goes. So this is the full equation for that reaction. Tin has been oxidized while silver has been reduced. Okay, so we are told to state the spontaneity status. What is the spontaneity status? The spontaneity status, since our answer is positive, spontaneity status. Since our answer is positive, then it means that the reaction is going to be spontaneous. So the reaction is going to be spontaneous since our E is positive, 0.94 volts, 0.94 volts. It means our reaction is going to be spontaneous. Okay, we have seen that. Now we look at the following STS for you. So this are STS for you, dear students. You're going to go ahead now, answer the following questions, and send your answers to us. So you have to write all the cell reactions for these two questions and go ahead to determine the spontaneity of the reaction. So this is actually what is expected of you to do. So with that, we have come to the conclusion of the spontaneity of a given reaction.